Welcome to AgScience-on-Tap. My name is Monica Egger, and I'm a professor for urban productive ecosystems here at the TUM. And for the last 2 years, I think now we're 2 years, we've been leading this Ag-on-Tap series here at Furtner, where during the semester, every month, we bring a speaker to present their work to what we call a lay audience. So people that don't necessarily know hello, Kevin, that know much about the topic per se. There may be some experts in the room, and then they have to ask the really, really hard questions. So today we have our second speaker in our series this semester that we've called, what have we called it? Like understanding models. I've already forgotten it. I'm sorry, Claudia. So I'm representing also Claudia Lux from the Hans Eisenman Forum. So usually we are here zu zweit or we are here together and host this event. So this semester we want to talk all about models and agricultural models and have these smart people explain these fancy models that they use to us. And we get to sit back and drink beer, eat chips, hang out, and learn from them, and then get to ask them questions. So today we have Professor Bernhard Schauberger, who is at the University of Applied Sciences in Weihenstephan-Triesdorf. And he'll present his own title, but he has a background in statistical yield modeling, the impact of extreme events on agricultural productivity, systemic modeling of value chains, and the attribution of climate change related to agricultural damages. So he has a very colorful CV where he has been around Germany, but also in France, and has been now with us in Freising since 2021. So we just found out I beat him by a semester. Yes. So where he holds a professor for agricultural systems and climate change. And before that, he was a postdoctoral researcher at the Potsdam Institute for Climate Impacts Research in Berlin, Germany. And also was then, before that, a postdoc researcher in France and was looking at the research on climate change impacts on agriculture at the Laboratoire des Sciences. Something French. Something French. Americans can't pronounce French names. And before that, did his PhD in agricultural economics at the Humboldt University of Berlin and Potsdam Institute for Climate Impacts Research. So again, at the PIC. So we are very happy to have him back in Bavaria, since this is where his roots are, back from Berlin. And we're excited also to hear him present his research titled Multi-Scale Models for Mastering Agriculture from Ångström to the Anthropocene. So thank you very much for being with us here today, and we're looking forward to your talk.
Thanks, Monica, for the intro. Okay, and what I will present today is the most arrogant talk I ever gave because it's all about me. But maybe we find something to discuss anyway. It's a very cryptic title, and I just try to compress everything that I did or do into one big thing, because I was asked to talk about models, and I think models is all my life. So what should I do? And so it doesn't work. Huh? So you already introduced me, and so that's just my own slide. So I'm here, not far away that's the HSWT. Exactly, my building is not on the photo. And that's the PIC where I'm still affiliated as a senior scientist because it's very helpful for my research that I want to carry out. And these are my research areas: risks in agriculture, trying to understand what climate change does with agriculture, but also the other way around. So seeing what agriculture does to the climate. And something very new that we started at PIC more or less 1 year ago, where I also have a slide which is called attribution. So if we have a crop loss, do we know whether it's from climate change? Yeah, and as mentioned, it's all very Bernhard-centric. So it's me, myself, and the models. And when I started to think about what to present, I thought, okay, I need a structure, and the structure is my life in different resolutions. So and here you have the Ångström, so the smallest unit you can have for molecules, for example. It goes down to megameters, so that's the global level, and everything in between is somewhat touched, and it's all from my childhood to today. And the first model that I had was this one. So all of you know that it's Lego. Then it continued to smaller scales. So Rubisco is a very important photosynthetic enzyme. The stem cells, so nothing on agriculture, but still relevant for modeling. Then I quit science because I thought I'd never go back to science. I don't like it anymore. It was very strange. And then I worked for 2.5 years near Lake Chiemsee and did some practical work there. But then I thought, okay, I do like science, but just in a different field. So I went back to science and started again with small molecules, but also went up to the global level. So that's the natural resolution of PIC in Potsdam. It's in Potsdam, not Berlin. That should never be mistaken. That's why it's called Potsdam Institute. Yeah. And then after my PhD in 2018, I had some postdoc years at PIC. And then in 2021, I came to HSWT, where I did a lot of different things on different resolutions. So starting from somewhere, going a dip down and then up again, I try to combine all resolutions in one, which is sometimes quite a lot of work, but let's see. And it's all in the Anthropocene. So I needed an A for the title, so that's where I put it. So, but there's not much to say. And now that's why I needed my own laptop for the Zoom features. So since this is about models, I want to start with a very coarse definition slide. So what models are and what they are not. So a model is an abstraction, a simplification of a system or of the real world that exists somewhere out, and we want to describe it. And it contains elements, so bubbles and interactions, so arrows between these bubbles, very shortly. And the model should describe the real world in such a way that when you change something in the model, it should be transferable back to the real world. So for people like Central to also live brief models, they know that. But for me, it was a long time not clear what a model actually is. So I tried to find this definition. And there are all kinds of models now. So this here, my daughters, they start with that one now, trying to change the hairdo and the dressing, whatever, and see if it is transferable to the real world. If you make a different hairdoing, does it look better or worse? And can we transfer it back to the real world? Or does this pullover fit to the eye color, whatever? The models that I look more are something like that, a regression model or the farm. So trying to see where inputs come from, where outputs go to, what it means for the climate and what the climate does to the farm. So it's difficult to play with Playmobil models in that way, but that's at least the system that I look at. And that's an extraction from LPGML. Central, you should know that. The typical LPGML cell, which will come later. And there are a lot of things that you can do with these models, but there's also one thing that cannot be transferred to the real world. For example, if you break this Lego guy, he doesn't care. So you just reassemble it and think, okay, I can break people and reassemble them and they are fine. Well, that's not the case. So models have limits, and this will be a separate section in the end. Clear so far? Yeah, I guess. Also not super difficult until now. Okay, and so I studied bioinformatics, where I learned a lot about how to model things and how to do statistics and try to abstract from biological phenomena. And one thing I worked a lot, so for more than 6 years, I wrote software for understanding blood cell lineages. So all of you have 120 million red blood cells that are produced very frequently, and they help you a lot to transport oxygen to the brain and all the organs that you need. And you have white blood cells that fight infections and all the things. And all these blood cells, they start from one progenitor, the so-called stem cell, hematopoietic stem cells. That's shown here. So you start with one cell and they differentiate into different lineages. So there are roughly 10 different blood cell types. And it's a very elusive question how they take these decisions, which blood cell to become, a white one, a red one, a macrophage, or any different blood cell. And what they did in this laboratory at the Helmholtz Center in Munich, they made images of cells. So looking at cells that did not live in the real mice or humans, but looking at them. And I helped to write a software that could analyze these decisions. So that's Tim's tracking tool was the PI of that lab then. And it's important, for example, to understand and cure leukemia. So to understand how blood cells develop and where they go to aberrant ways into cancer. So we need to understand that in order to develop medicines. And I showed it because there are models on 2 levels here. The first one is the cell in the Petri dish, which is somewhat a real cell, but it's not in the living system. So this is the first level model that changes maybe a lot, because what you do to the cell in the Petri dish is not necessarily transferable to the real world. So if a medicine, like with the corona vaccine, if it works in a Petri dish, it doesn't mean that it's good for people. And there's a second level of models, which is the cells that, taking the movies I have in my software. So that's even more abstraction and absolutely not clear whether you can develop a medicine with that. So that's how I learned models. And in agriculture, it's not so much different. So the plants that we grow in our vertical chambers, they are maybe different from the ones outside. And particularly if we even model them, they're very different. And maybe we can learn something from the models in the computer, but maybe not. Maybe it's just nonsense. So we always should be aware of the limits. So we are already in my studies and now at work, because I said I quit science because I didn't want to do this hematopoietic stem cell modeling anymore. I thought that if that is science, then I go. And so I went to Lake Chiemsee. So that's a renewable energy facility where I was selling wood chips and pellets and driving all around Europe and telling mayors in Czech Republic and Ireland how good bioenergy actually is. So wooden bioenergy, because now in my lectures I say the opposite. No, bioenergy is not a good option for different reasons. At least for the woody ones, I still stay consistent with my past and say, okay, wood for energetic use, if it's the waste wood, that's fine. But first, make furniture and houses, and at the end of their lifetime, burn the houses. That's okay. But not there's a limit to bioenergy. But that's on another slide, on another topic, not another slide. Yeah, and here this is one example of my little research that I did. So that's a container where you put a lot of wood chips in, and they need to have a certain dryness level below 20% to put them into the oven in small houses. And if they don't reach it, they start to mold and you cannot heat them. And so we tried different of these containers and put them at the combined heat and power plant and thought, okay, let's try them, and that's fine. It's easy in theory, but absolutely not easy in practice, because there are a lot of different containers. Then what do you do with the wood chips that are still moist on the top, but at the bottom they're already dry? So it gets easily very complex. So again, you need a model how to understand, to help to understand how to do this drying. And also, so that's, I don't know if you ever heard the word heat pipe. Do you know heat pipes? No? So that's, I also didn't know before, so that's okay. That's somewhere in Siberia, I guess. And they use them for pipelines, because in the permafrost soil, when you have pipelines, they're usually warmer than the soil, and they would melt the permafrost. So they need to transport the heat from the pipelines away into the air. And for this, they use heat pipes because they are very efficient convectors of heat. So that's inside, it's a little liquid, there's a little bit of liquid, and it gasifies here, transports the heat up, and releases it into the air. So it's very efficient, much more efficient than anything you have in your computer as a cooler. And what people thought, let's put these heat pipes into a so-called wood gasification plant. A wood gasification is an incomplete burning of wood where you just don't harvest the heat, but also the gas. So you can make, in the end, plastic from wood. For this, you need to gasify it. And they thought we do it to harvest the energy, so make electricity from wood in a very efficient way. Theory, very nice. Practice, the company went bankrupt. So it didn't work because their model plant that they built somewhere in Austria worked fine. But when they transferred it to a larger scale here at Chiemsee, it just didn't work at all. So again, also practical models where you think, okay, they're easy, you build them, you scale them up, and then just calculate the economy. It's the same. They have a lot of hurdles and failures or possibilities to fail, and don't think it's easier to make a model that you can touch than a software model. And so at the end, I just skipped it. In the end, I thought, okay, science is not so bad. I go back to science, and that's what I did then, starting a PhD at PIC in Potsdam. So I don't know. I guess there cannot be too many questions, but if you have one. then please feel free. Because I'm talking rather quickly, I guess. It's okay. You can listen quickly.
It's a lot more interesting than a piece of paper Lebenslauf. So
okay. So again, now spanning a very large scale of resolution. So 03, who knows what that is? Ozone, exactly. Is it good or is it bad? Is ozone an angel or a devil? Yeah, exactly. So in the troposphere, it's bad. It damages your lungs and the photosynthetic organs of the plants. But if it's in the stratosphere, it blocks the UV radiation that we don't want. Okay, back to models. Now only software, never touching a plant again. And what you see here is the world in pixels. And that's how the model that I used at PIC, LPGML, is looking at the world. So it's an agricultural model. It's much more, but also agriculture. And it divides the world into very small pixels. And they are not so small. They are 50 by 50 kilometers. And for a long time, this was the smallest field that I knew. So any farmer would say, what do you want to tell me? Your field is way too large. What can I learn from that? Hello. But still, global models have their relevance because you need to understand global connections. And if you want to run a global model, you cannot do it on very single plant scale. So you need to make an abstraction, make a simplification. So it's written in C and very fast, much faster than DSAT, I would say. Well, yeah, and it's actually a nice model. And what I did with this model, I implemented an ozone damage module. Because when you look at the path, that's ozone outside somewhere in the air. And it enters the plant leaves via the stomata because they need to open the stomata to allow CO2 to enter and water to go out and also oxygen to go out. But if there's ozone in the ambient air, it also can enter into the stomata. And this ozone is damaging. So a part of it goes away to null, but it's fine. But the rest stays there and has two damaging effects. The short term, because it binds to rubisco and destroys the photosynthetic enzyme. So no more photosynthesis possible. And it also advances the senescence of the plant. So the plants grow old faster. And thus they cannot accumulate as much biomass and thus also not as much yield as they should do. So that means a high ozone level in the outside air is not just bad for you if you go running, but also very bad for plants. And how bad it really is, it was a long time unknown because it depends a lot on water. The more water a plant has, the less damaging ozone is because it needs to open the stomata less. No, sorry, the opposite. No? If a plant has a lot of water, it will usually open the stomata more because it can transpire and grow better. But more widely or more frequently open stomata also allow more ozone to enter. So you do irrigate the plant because you want to have high yields, but at the same time you take the ozone penalty into your economies. And also CO2, if CO2 concentration rises, the stomata go close a little bit because they don't need to open as much. And so ozone is entering a little bit less. And what I did is implementing this in a global model and trying to see, okay, what happens on the globe if we take current ozone concentrations. And that's what you see, that's for winter wheat in different countries. So you see the relative loss compared to null ozone is pretty high, even for countries like Germany. I'm not sure how much to trust the model here. Maybe it's a bit of an overestimation, also depends on the ozone models that are in the background. But it's a substantial share. Australia has a low ozone concentration here, so there's little damage. But if it also shows that if we reduce our ozone pollution, which comes, for example, from unclean VW cars, so it was a part of the diesel scandal, we could gain a lot more yield without anything else. So just the same plants, just the same growing conditions, but no ozone, would give us a higher yield and a better health in addition. So that's the Western world, more or less. But now if we look at Asia, they have a double penalty. They have much higher ozone levels and more sensitive plants. Strange enough, so they have different wheat varieties that are more sensitive to ozone, plus the higher concentration outside gives an extremely high penalty, particularly in India, up to 40% yield loss due to ozone. But that's a bit awkward, because if you say that air pollution is a problem anyway, so fine particulate matter in India is partly extremely highly concentrated, would be a benefit for human health, but also for plant productivity if it's reduced. So putting filters on the chimneys, on the cars and everything. So they could gain a lot. And they do have a harvest problem, or they run into one, because they have a huge population. They need to irrigate almost every field in the highly productive north. So they do have an agricultural problem coming up as well. So we need to increase productivity on the existing land. And this would be one option, reduce the air pollution. So that was one practical derivation that I had from my models. Don't know if it was ever implemented. Surely not based on my work. So that was the PhD. I don't know, any questions? No? Well, it depends. So here for the ozone, I read a lot of studies, and then there are many more processes, but I had to select those that I could implement, and where I also had data to calibrate them. So I would say the physiology is more complex, but it doesn't mean that I understand it. So that was enough for me with these three arrows. Okay. So PhD is over, science is still nice, so I do a postdoc. And I showed this slide for a different reason, but I thought it fits here, that agriculture is not so easy. So what we want in agriculture is yield. So tons per hectare, the higher the better. It's composed from biomass, so the total biomass of the plant times the harvest index, so how much of the biomass you can actually eat or give to the cows or whatever. So two factors, but they are not determined at harvest stage, but they grow over a long time. So they start with the sowing, and then there's the vegetative phase and the generative phase, the reproductive one, where the grains are produced and filled. And these again are influenced by a lot of different things, by weather, by management, by pests and diseases, by soil attributes, but they are just categories. So there are a lot more subcategories. They all have an influence on this plant growth. And again, above all, there's climate. And even before climate, we have a box which is called CO2 or emissions and aerosols. So coming back to the aerosol thing, ozone not, but other fine particulate matter is actually nice for us in that context because it cools the climate. So if we now tell India or other Asian countries to reduce the air pollution, they will have a little more warming, local warming. But I guess the health benefits of reducing air pollution are much higher than this little bit of additional warming. And all these things are connected. So you can draw a lot more arrows here, basically between everything. And now the question is, if yields go down, so if we don't have the harvest at the field that we want to have, what went wrong? And it's a pretty complex thing, because maybe we know there were pests and diseases, but then we have to ask, okay, why were they there? And there was this case in 2016 for France, where pests and diseases were much more prevalent than usual. So they had to ask, okay, what was the problem? And then they found out, okay, it was the climate in spring and in winter, which reduced grain size and I think also grain weight. So it's a pretty complex thing. If you want to know the reason why yields go down, we need a model that at best understands all these physiological connections. But we don't have it. We can only model parts of it. We can look particularly at the soil, maybe at the humus content, at the microbiology, But then we need to neglect the management things because the model would just explode with connections and we don't have the data to calibrate it. So for each model, for each research question that you have, you need a different model looking at different aspects of this enigma. Still, if you have a nice model, you can maybe influence policy a little bit. And I would like to show this with 4 different examples. 3 of them are so-called early warning systems, something that we worked on at PIC and work that is also still ongoing. Because if that was here, it's CLIMSEC, it was funded by the Auswärtige Amt, by the Foreign Office. Hello. Hey. Because they know that in West Africa, there's a lot of conflict between farmers and herders. So the farmers, they're usually nomadic, they make transhumance, they follow certain routes that also go along agricultural fields. But if the farmers already had a low harvest, there's little left to feed the cows that come from the nomadic farmers. And when this happens, a lot of conflicts come up very quickly because they're usually separated along ethnic lines. So the nomads are, for example, Fulani, and the farmers are another ethnicity. And so it's just a fight about biomass, but it easily escalates into an ethnic conflict. And so the Foreign Office, always being interested in preventing conflicts, asked whether it's possible to make an early warning signal that tells, look, biomass is low, it's on a transhumance route, farmers are there, nomadic herders will come, potentially a conflict source. So they asked us whether we could write such a model that could inform them. So we tried. I'm not sure whether they use our work. That's up to them. But at least we could find something. And what you see here is a so-called Bayesian belief network. And it was made with farmers. So they, of course, they don't know what a Bayesian belief network is, but they got a lot of boxes and drawings and they were asked, what do you think is connected? And they said, there's soil, there are other people, there's this another village, and they make a lot of different errors. And then in the end, there were, I don't know, 40 or 50 responses of very different connections and boxes. And we tried to compile it into one, making this Bayesian belief network. And it's still ongoing work to put this into a real model. And I'm not sure what we do with that, but at least we know that this early warning is also at the refugee part of the UN, also very relevant issue. Also the FuseNet to predict famines early on, food insecurity problems. And this one here I find most interesting because the DARPA is the research arm of the US military. So maybe you know it, no? And we had a project, it was orchestrated, maybe you know it as well, by Joshua Elliott, no? And they launched a program with $70 million to make a so-called world model that also does this forecasting, early warning of many different aspects of food security. And it was crazy. So there were 100 researchers and everyone completely different disciplines and ideas and what to do. And we all tried to merge that. So I was just a small stone in that system. But there were people who tried to merge that. And out came this dashboard, the World Modelers dashboard. And you can see a lot of different things that you can arrange, but I'm not aware of any use of it at the moment. No? We tried this with Ethiopia, so the map is in India, of course, but we tried this with Ethiopia to see whether we can successfully hindcast past crisis. It's, of course, all built on models. So we participated with LPGML, and others participated with very, very different models. So for me, it was a nice learning experience. And I thought better they spent the money on us than on weapons, but still it was a military funding. Yeah? And one project is called Agrica. It's done at PIC. It's still ongoing, and it's for many, many different countries in Africa looking at climate risk and how to adapt to that, particularly on agriculture, but also on the health sector and other things. And if you go to the Agrica website, it's agrica.de, you can download a lot of these small profiles. So they're just 4 to 10 pages for each country, and there are longer analyses looking at how to adapt. And all this again, based on models, and it was always played out at very high levels, so up to the ministry telling what to do, or what risks there are, and what they could do about it. Whether they do it, I don't know. At least they listen. So the models, they started very abstract, but now getting into policy, they become very concrete. And if you think that the model that you construct may be wrong, leading to possibly a wrong decision, saying, look, there's a conflict and all the soldiers go there to prevent it, but suddenly pops up at a very different place because your biomass calculation was wrong, then it's also an ethnic issue, no? So you want to be correct in that way. And one of the basic ingredients of models is, apart from the equations, is data. And what I will show you here, so it starts like a James Bond movie. Now it's in northern Ghana, one of the counties there, Bilsa district. And you will see different curves for maize. So it's an anomalies over time. And you see it's a complete, it doesn't match anywhere. No? So different sources. So that's the official data in black. Amplify is a very simple statistical model that we constructed. UpSim is a very respected crop model that we had. And we also used satellite data, the NDVI. And you see they don't match anywhere. Each of these tells a different story, whether it's up or down. They don't match in the amplitude, they don't match in the direction. And then I presented this at the poster in Budapest, and by chance there was somebody from the Ghanaian Ministry for Agriculture, and he said, oh, why do you use our data? They are crap. But it's their official data. So I asked, okay, what should I do then? Oh, well, don't use our data. Okay, then I won't use your data, but well, what else should I use? Because if you want to construct a model where we base decisions on saying how to adapt maize production to climate change, for example, we cannot do that if we don't have the proper ground data, because maybe we get completely nonsense correlations out of that. And so here I started to develop a correction algorithm. So I started it in 2019. If I extrapolate my progress linearly, I will finish it in 2031 to find out which one is the correct one. So that's the question. And if there's a lot of mismatch and geographic misinformation, if we cannot trust the official data, then we have a problem because we don't know how to calibrate our models. We can have the best of equations, but if you don't have any data to fit them to, we don't learn anything, and we just can make wrong conclusions.
So what goes into the correction algorithm? How are you verifying that information?
Yeah, I don't have a slide on that. So what I thought is also a Bayesian network. Trying to find all the data sources that I have, also the official data, but satellites, surveys, crop models, whatever data I have, and throw it all into a Bayesian network and find out which actual yield is the most probable one. But it's work in progress. So I started to do this in the US because I think that the US data is reliable. And so I distorted the US data, and my algorithm was able to reconstruct that. But at that point I stopped. So because now I would have to transfer it to Ghana. But I don't dare to. Okay. So I have a lot of slides and a lot of talking, but yeah, it's not so much left anymore. So the one question that I always get asked by students is, okay, I believe climate change is there. I believe it's a problem for us, but what should I do? So tell me what to do and I will do. The problem is I don't know. So that's what's written here. I believe you, but please, my farm looks like this and that. I have 20 cows and 50 hectares of something. What should I do? Well, and then the question, the problem is back to me, and I don't know, because there are so many different scales of agriculture. Maybe you find an idea for this field, but then the weather next year is different again. Or maybe you say, okay, we need to adapt the European CAP policy into a certain direction, but suddenly farmers say, okay, if the cap looks like that, I give up my business. And then we have one large farm all over all of Europe, and the others just give up because they say it's not economical anymore. And so we need to consider a lot of different things when doing recommendations. So I am in a fine position. I just say, I don't know, go find yourself. But maybe I can give you some guidelines. And that's one of our approaches that we have now. It's called ERATRO. It's erfolgreiche Ackerbaustrategien für bayerische Trockenlagen. So looking at Bavarian dry regions in Franconia. Raimund is actually participating there. And what we want to do is we want to ask the farmers. So this is this part here. Okay, several of the last years were really dry. 2018, 2019 also a bit, particularly 2022. And we asked them, what did you do in these years? Did you try anything new? Did you use different machinery? Did you use cover crops? We asked them whatever they did, even if they just put an electro plug into the soil, the electroculture. So it's a nice joke on the side. We just asked, what did you do and how was the yield? And if we asked many farmers, then we get maybe a picture of what works under drought. So we don't use any models at that point. We don't use any hypothesis from our side. We just ask the farmers, what did you do when it was dry? And second question, did it work? Did you have normal yields? Did you have even above average yields, particularly when looking at the neighbors that all go down, but you go up? And then we collect all that data and analyze it. And that's ongoing. So just yesterday we had our first interview, and now we plan to roll it out to many farmers in Franconia, because that's the driest region of Bavaria. But then we don't stop at the interviews. We try to combine it with a lot of different data from these sources. Also, we want to do our own field experiments. So if we find out from the farmers that something works, we want to try it if it really works. And literature and experience from other regions, and all combine it into a practical guideline for farmers. Okay, look, drought is a problem. That's a set of measures. They're not 100% fail-safe, but a lot of farmers have tried. There's a scientific basis for that. So please go and try. That's the idea, but it has only started recently. So again, I cannot tell you anything what to do. Then agroforestry, maybe some of you have heard of that. Agroforestry is a good idea for many fields, for many different crops. We planted one at the HSWT in May, and this Saturday we will plant the second part of it. So it will be nice weather for planting then. And it looks like this. So it's a very steep field, and we plant rows in between to stop erosion, partly, but also to sequester carbon into the soil. But agroforestry is actually a complete different topic. The only thing that matters here in this context is there are little to no models. So how to model agroforestry? Well, you have the tree models and you have the agricultural models in between, but nothing that really does agroforestry modeling. So that's a gap that Michaela, who is just finishing a master thesis and will do a PhD, wants to complement. Maybe I just skipped that. So vertical agri-PV, maybe you've heard, but there are a lot of open questions. Yeah, and this was the one that I alluded to in the beginning, attribution. So assume the maize yield is much lower than usual in Kenya or anywhere in the world, just took one country. The question is, was it due to climate change? Well, how could we answer that? We first have to check, was there bad weather? In that sense, for example, a very high temperature, a storm, or a drought, whatever, anything that was bad for the crop. If there was, the second question is, was this bad weather actually the cause for the yield loss? Because only then we can continue. Or was it just bad management? So was the yield low because the farmer didn't put enough nitrogen, but the weather was actually nice? Could have allowed a good yield. And we also need to stop. But if all the things, except this one here, are yes, then we need to go further, one step further. So if we observe bad weather, which was causal for the yield loss, was this bad weather due to climate change? Maybe those who are German, they heard it a few weeks ago. There was the Deutsche Umweltpreis awarded to Freddy Otto, who pushed this attribution science very much. She developed a lot of methods to assess whether a heat wave, a drought wave, whatever, is actually caused by climate change. So you can never be sure, but you can calculate probabilities. So this link here is more or less established, particularly for heat waves and partly also for droughts or late frost. So we can draw on existing science. But then again, we are not done. So if we say, okay, all this chain here is yes, due to climate change, we still need to ask one question more. Was this part of climate change a natural variation? Or was it really human climate change, anthropogenic climate change? Because then if all of these chains are answered with yes, the question is how much should we pay? Because we cause climate change, the farmer in Kenya suffers. And this is the question that dominates the COPs, so this climate conferences at the moment, loss and damage, because it's extremely political. Of course, nobody wants to pay, or others want money for good reason. Others don't want to pay for some reason, but it's a political and economic question. And as you can imagine, there are a lot of questions and unknowns here. So it's a completely new field of science. So this one here is established for a few years now, and it's accepted, even in legal claims now. But all the other things, of course, there's models, there's science behind, but to combine it all into one is, yeah, it's going into the wild. We see how much we achieve, but at least there was a FAO report out in October where we contributed and looking at different countries, seeing whether they have had yield gains or yield losses due to climate change. And so for some countries, there's already a statement possible that climate change was actually bad, and for some others it was also good. So it's not uniformly bad, at least for some countries and some crops. Mostly it is, but not everywhere. And I think, yeah, that's a wonderful puzzle if you combine it. I'm not yet done now, so a few minutes left. We should combine knowledge on all scales, models on all scales, because only then we can master the Anthropocene. No, it's deleted now. Okay. There will not be one model to rule them all. And water is key. That's what I learned. So wherever you look at, if you ask farmers, what's your most pressing issue? They always say water, either too few or too much. So proper water management for Germany now is the thing we need to develop in practice and in models. Okay, now we've seen a lot of applications of models. That's, as mentioned in the beginning, there are some caveats. And something maybe the people from my lectures, they know it. That's the universal soil loss equation. So if you look at this field, it doesn't look nice anymore because there was a torrential rain coming down and taking away a lot of the soil. And this is, so that's the German abbreviations, but doesn't matter. That's a way how to calculate the erosion. So the tons per hectare that you lose due to erosion events, be it wind, so that's your water. You can also do it for wind. And this is a model now, and it's calibrated for a certain amount of rainfall. So if you live close to the mountains here in the Alps, then you have a higher rain erosivity than somewhere in Franconia. But there are limits. So if there's really a lot of rain, then the model maybe just doesn't work anymore. It tells you there's an erosion, but it doesn't capture it if the full field is just gone. So there's a model limit, and if it's even more, so a comet is hitting us, the model is certainly inadequate. So it's very unlikely, but particularly for climate change, we cannot rule out the extreme borders of the projections. So we should, particularly for climate change, be aware that the extreme realizations are also not impossible. And then maybe our models are just crap, because we don't consider that. And then I like this picture, billiard. It's an example for the butterfly effect. So billiard is perfectly calculable. So you know you have to push the white button, the white ball, and it has to kick the others into the holes. And up to the second level, so white ball, color ball 1, color ball 2, it's perfectly calculable by any model. It's a simple physics. But if you go to the 9th level, so 9 chain reactions ahead, you even need to consider the gravitational force of the people around the table, because they influence the movement of the ball. It's still rather simple physics. but it's completely intractable. And the same here for models. So we know a lot about plants, but we cannot just put it into the model because the runtime is too high, the data requirements are too high. And so we have a lot more knowledge maybe than our models do. Still, we cannot put it into one model. And this realization I also like. I took it from a book by Nassim Taleb. If you change the initial conditions, if you have a good model and you change the initial conditions a very little bit, then maybe the outcome is completely different. And so this is not one line, it's several lines, but they are only very slightly apart, okay? Which you don't even see that with your eye. Now they are reflected, it looks already a little bit different. Now they're reflected again and again. Oh. So a very slight change in initial conditions produces huge differences in outcomes. So that's the initial value problem. In climate projections, they try to tackle it with explicitly perturbing the physics to see how much projections change if they change the model a little bit. It's also a butterfly effect. And that's my final sentence. All models are wrong, but some are useful. And the question is, how wrong need they be to be not useful anymore? Yeah, okay. I even have more work. It doesn't matter. So thanks for listening.